Alright, it should be working.
One of the most important is
Alright, we are going to get started on making our final cheat sheet. It's not literally cheating, it's called cheat sheet, but in reality, it is a reference sheet that I can use on my phone, and we're allowed to. I'm going to make it double-sided. Yeah, it's going to be a long night. We got 2 finals tomorrow. Those are the last finals I have this semester. After that, I'm done with the semester. I got the whole summer then. I can't wait. I gotta get back on working out. I haven't been working out for like the past 2.5 weeks just with finals and all that kind of stuff. So I'm excited. But let's get to it. Alright, so first things first, we're covering lessons 16 through 22 on this final. I'm so glad it's not covering the entire course, or I would not be a happy camper. So lesson 16 is polynomial fitting for recurrence relationships. Okay. Oh, we got another one of these. I have to show you the stream thing. We got all the bots going up there. Okay. Let's see. Okay, I would share my screen, but my computer is going too slow to be able to share my screen while I stream. I've already gone through this and tried this, and it just don't work. Man, I feel like I'm getting so skinny right now. I'm losing all my definition. Just 2 weeks ago, I felt like I was jacked. That's all it takes. 2 weeks, 3 weeks of not working out. I mean, I don't think I'm actually jacked, but after I think it's because when you stop working out for a couple weeks, you lose all your water weight stuff. Your muscles kind of get a little less deflated, but they deflate, and I think they actually deflate a good amount. Because all it takes is I've experienced this before. I'm used to the feeling because I work out as much as I can, but there are times where I'm super busy. I'm not going to stress about it, so sometimes I'll go a couple weeks without it. And when that happens, I feel like I do right now, where I feel like, oh my god, I'm getting tiny. My arms are a little tiny, all that. But every time I've experienced that, it just takes about a week to start feeling good, and then about 3 weeks of consistency to start feeling fantastic again, about just size and mentally. But I'll leave it at that. So let's get to. I'm kind of procrastinating here a little bit, if I'm being honest with you. So that's lesson 16. This one's going to be interesting. So this is about polynomial fitting. Okay, polynomial fitting for recurrence relations. So what this should be describing is when you have sets of data. When we have sets of data and we want to just create a function out of that set. So you have a table saying here's a time and here's how far a runner was at this time, and then creating a function out of that. And what we're doing here, I'm sure it's actually super basic. And some of the stuff I should know, but I just don't, just because I was a lot of personal stuff going on this semester. No excuses though. Actually, I guess that is an excuse.
A lot of times when we're solving
You guys might hear that. I'm going to be rewatching my professor's videos right now.
turns out there is sometimes a way to actually solve a recurrence relation by using what's called polynomial fitting. So a polynomial we've seen before, a linear function is a form of a polynomial, quadratics, cubics, quartics, all those guys are forms of polynomials.
Oh, and I can't wait to get out from behind the screen. Tomorrow's the last day. We got the whole summer.
Is any function of the form f of x equals a sub k times x to the k plus a sub k minus 1, x to the k minus 1, all the way down to this constant. So we'll point out here that a0 through ak, those are just coefficients. They're just some real numbered coefficients. And we call this a kth degree polynomial because notice that the highest power is k. Also,
So a kth degree polynomial is any function of the form f of x.
And
Okay.
I'm kind of alluding to what
That
we've
makes
already
sense.
learned before in terms of polynomials, but
So a
all
kth
of
degree
these powers,
polynomial
all of
is
these powers
describing a
equals
polynomial of
one
any
here.
size,
You actually
basically.
think about
It could be
this
a
as having
second degree
x
polynomial,
to the
third,
zero,
fourth, fifth, so on and so
sub
forth.
zero.
So it's going to be a constant times a variable that has k as an exponent. If it's a third degree polynomial, it will
Positive
be
integers. Or I
a
should say not positive, but integers
to the power of
are
k
bigger than or
plus
to 0.
ax to the power of k.
So
Oh wait, what did I
examples
say?
of this
Minus,
would
oh,
be
minus
writing
1, yeah.
y equals
Plus ax to the power of k
plus 1.
minus 1 again
And so in the
until
context of this, notice that it's really just these.
it's like saying like a
where I
cubed
guess
or
I'll
x
call
cubed
this
plus
A1
x squared
or
plus
this
x type thing.
0. This is a linear function here. And then we could, of course, have a quadratic. We could say 3x squared plus 4x plus 5. This would be quadratic. And that would be the first 3 terms. So this term right here would technically be a0, and this would be a1, and this would be a2. The reason we label the subscripts in descending order is just so that the subscript matches the exponent. Just a nice little convention there. Now, of course, we could also have cubic. We could have 8x cubed plus 3x squared. And maybe we don't even have the linear term, we just have plus 1. In that case, you could actually fill in 0x here to the first power so that you would have a0, a1.
It's a little fidget spinner.
Okay, so the notation isn't that important. The idea here is just that this is a general way of writing a kth degree polynomial. Now, the cool thing about polynomials is that they have constant kth differences.
So do I understand this?
Look at a couple of examples.
They have, it says, a key feature of a kth degree polynomial is that it has constant kth differences. You write, oh wait, isn't there notes that... Oh, okay, there is, very nice. A kth degree polynomial is a function. Any function, okay, we know what that is. A key feature of kth degree polynomial is it has constant kth differences. Okay, I don't understand. I probably know what that is, but I don't
We
understand what
write
it means.
a polynomial that is a kth degree polynomial. We call it a delta k constant. This is the same symbol that we
Oh,
talked about.
then it goes
back
down
in
1
the
power every. Yeah.
Okay, what does that mean? Well, let's take a look at a table
Delta
of
K-
x versus y.
K
So this is
constant probably
our
means
old
that.
way of function thinking. And let's say y is
Maybe I'm
equal
wrong. Let's
to
see.
2x plus 1. And we look at some values of x. Now, it doesn't really even matter what these are, just as long as they're evenly spaced. If this jumps from 1 to 7, but then from 7 to 8, then the x values aren't equally spaced. The important part is that our y values are separated by the same increment in x, but we're not going to get too deep into that. So this would be 3, and then we'd have 5, have 7, 9, and 11. Now, we would say that a linear function, okay, a linear function is a first degree polynomial. So we would say that this is delta 1 constant. And all that means is that if you take a look at the differences between your y values, the y values in this case grow by a constant value. So notice that the very first difference that you take of the y's, the difference is already constant. So these are constant first differences. What if it were a quadratic? Well, in the case of a quadratic, you should have constant second differences. Now, how do you find second differences? Okay, let's just say, I'm going to keep this real simple. We'll say we have 2x squared plus 1. That's a quadratic, is the second degree polynomial. We would say this is delta 2 constant. And again, let's just look at a few x values here. So we have 2 plus 1 is 3, and then we have 2 times 4, which is 8, plus 1 is 9. 3 would be 18 plus 1, which is 19, 4 squared is 16, 32 plus 1 is 33, 5 squared is 25, times 2 is 50, plus 1 is 51. Now if you take a look at the first differences, here we get a difference of 6, a change in y of 6. Now y grows from 9 to 19, that's a difference of 10. Then the y value grows by 14, and then the y value grows by, 18. I think so. That looks right. Okay. Now you notice that this is the first difference, but the first differences aren't constant. The first differences are changing. Okay, so this is the first difference. Notice that it's not constant. Now, if we take a look at the second difference, in other words, we look at the difference in the differences. Well, now, from 6 to 10, that's a change in the rate of change of 4 units. Here, the change is 4, and here, the change is 4. And now notice that we have constant second differences. And so that's what we mean to say, when we say delta 2 constant. Thing about the relationship between this and what we've actually seen in our introductory calculus course is this is actually a way of thinking about derivatives. If you take a look at the derivative of a function, if you take a look at the derivative of this guy here, dy dx, okay, by the power rule, the derivative of 2x would be 2. The derivative or the rate of change of a constant is 0 because it's not changing. And so notice that dy dx, the derivative, is in fact the constant difference. Same thing will work over here. If you take dy dx, by the power rule here, you'll get 4x, derivative of 1 is 0. So that's not constant. In fact, we could see that dy dx depends upon the value of x, and that makes sense because the dy dx is changing. Here the increase is by 6, then by 10, then by 14, then by 18. So our differences are actually getting bigger, and we do in fact see this when we would plot the function. We would actually see a parabolic, right? Something that is changing faster and faster and faster. But when you take the derivative of the derivative, which we would often write like this is not squared, this just means the derivative of the derivative. And that would give us 4. Okay, so that's exactly matches up with our second differences, which are constant. And once we take enough derivatives, well, we're going to end up with a constant as long as we start with the polynomial. And more specifically, a delta k constant, the kth derivative will be constant. So in our next video, we'll actually take a look at how we can use this to model data. Well, if we have a sequence, then find the closed form for that sequence as, the closed formula will be a degree k polynomial if and only if the sequence is delta k constant. So all we need to do, if I hand you a sequence of values, which we're just a little flash forward towards our example, if I would take a look at this sequence and I can figure out the differences, and I can figure out that the kth differences are constant, well then I can fit a polynomial to this data, and that's pretty easy to do with technology. So we'll take a look at that in the next video. We're going to end up with a constant as long as we start with the polynomial. And more specifically, a delta k constant, the kth derivative will be constant.
Okay. So I muted myself, or I thought I did. I muted myself, or I thought I did. But I guess I didn't. Damn, I got red shit all over me. I thought this whole time that I was using my other microphone. I thought I was using this, which is nice that it's not. Because I can just talk. Okay. Now when I play this. Okay. Sorry, I'm just testing out something. Okay. Well, there's not a lot of lag in my stream today. Okay.
So in our next video, we'll actually take a look at how we can use this to model data. Well, if we have a sequence, then find the closed form for that sequence as, the closed formula will be a degree k polynomial if and only if the sequence is delta k constant. So all we need to do, if I hand you a sequence of values, which here just a little flash forward towards our example, if I would take a look at this sequence and I can figure out the differences, and I can figure out that the kth differences are constant, well, then I can fit a polynomial to this data, and that's pretty easy to do with technology. So we'll take a look at that in the next video. So we have established now that as long as the sequence that we're dealing with is delta k constant,
Food.
we've got two ways that
Hungry.
the kth differences are constant, or you could look at it as the kth derivative is constant. That means the same thing. Unfortunately, we're not going to be able to take derivatives because we're given a data set, not a function. If you have a function, you can take a derivative just like we did up here, but the only way to look at a sequence is to actually compute those differences just like we did in red, and then in red and purple over here. So as long as we have a sequence that is delta k constant, then we can fit a degree k polynomial to that data. Let's take a look at how we're going to do this. Well, there are algebraic ways to do polynomial fitting. It does get pretty exhaustive because it usually results in a system of equations that needs to be solved, and then now you have a whole new algebraic problem to deal with. So we're going to actually take a look at doing this with technology because it's readily available and it's much more efficient. So we'll take a look at a couple of examples here, one which will not give us much context, and then we'll look at a contextual example which polynomial fitting will make a lot easier to solve. And I think it's example. Now right now, this form, A1, initial term being x equals 0. We've kind of done that. We've called our initial term A0 or x0. So let's go ahead and see how we can do this in Desmos. Okay, so here in Desmos, the first thing we want to do is actually enter our data in. As you can see, I've already done that, but let me show you how I did that. So we're going to clear this out, and we would first click on the Add Item button so that we can put in a table. By default, your very first table, your x and y values will be labeled x1 and y1. You don't want to, we would first click on the Add Item button so that we can put in a table. By default, your very first table, your x and y values will be labeled x1 and y1. You don't want to relabel these as x and y because x and y are system variables, and that will try to generate something over here in the plot. If you use the subscripting like it shows here, then these are actually assumed to just be data sets. So because we typically start our value at A0 or X0, whatever you want to call it, we would start here at 0, and as you can see, after you enter in 0, 1, it's going to auto put in the value for you. So we have 6 total points, 2, 3, 4, 2, 3, where are our values? 2, 3, 7, 14, 24, and 37. Okay, now to actually get this window, normally you're going to be from negative 10 to 10 on the x-axis. And so in order to see that data, click on the little wrench, and we'll set x to go from, say, 0 to 6, since that's just a little more than our x values go to, and we'll set y to go from, say, 0 to 40. And all I'm trying to do here is just visualize the data so I can see that this data is in fact quadratic. We'll zoom out a little bit, and you can see that that looks parabolic. It doesn't always mean that it's perfectly parabolic, but we've already checked the second differences, and we know that based upon that we have a delta 2 constant function. So now, in order to do the regression, we are now going to reference x1 and y1. And so we're going to actually sort of write an equation that's going to be of the form y equals something x squared plus something x plus something. And we want to reference y1, so we'll say y1, and you can see it references the 6-element list. Now, if you press equals, that's not going to do what you want. You actually want the little tilde, the little wiggle right here. And now you don't have to do a2 x squared, x1 squared. You could just do a x1, and now caret 2. So you have to do x1 squared. And you can already see that we get an estimate of the best fitting polynomial. This is called a regression analysis. And you can see here that it says, okay, for this black quadratic function, a should be about 1.5. Now you can see it's not a perfect fit. It doesn't go through all the points, and therefore it doesn't model our sequence perfectly. Plus something x plus. You can actually sort of write an equation that's going to be of the form y equals something x squared plus something x plus something. And we want to reference y1, so we'll say y1, and you can see it references the 6-element list. Now, if you press equals, that's not going to do what you want. You actually want the little tilde, the little wiggle right here. And now you don't have to do a2 x squared, x1 squared. You're not going to do y1, so we'll say y1, and you can see it references the 6-element list. Now, if you press equals, that's not going to do what you want. You actually want the little tilde, the little wiggle right here. And now you don't have to do a2 x squared, x1 squared. You could just do a x1, and now caret 2. Okay, so you have to do x1 squared. And you can already see that we get an estimate of the best fitting polynomial. This is called a regression analysis. And you can see here that it says, okay, for this black quadratic function, a should be about 1.5. Now you can see it's not a perfect fit. It doesn't go through all the points, and therefore it doesn't model our sequence perfectly. This value of r squared, the closer this thing is to 1, the better our fit is. If it's exactly equal to 1, then we have a perfect fit. Now we need the other terms, so let's do plus, we'll just say bx1, bx1. And, okay, let me take that power out of there. Now, we're a little bit better, 0.9948. You can see it's still not a perfect fit. We're still missing the initial point. And that's because our y-intercept is not there. So we'll say, let's come back over here. 0.9948. You can see it's still...
Here you go, buddy. Okay, I'm back. Okay. Caught me. You caught me. I just started looking at stupid freaking videos. Accident. I must have went down a rabbit hole there. They've been getting me these last few days. I haven't been watching any shorts for like months. And the last couple of days I just started. I think it's because I have finals. And I'm a little bit more tempted to distract myself right now, but here it is.
Not a perfect fit.
So, parameters. What A, B, and C should be.
So missing the initial point. That's because 5C is 5x. You have a delta 3 constant, then you want to have 3 terms in descending powers of x, and then your constant.
Okay, we understand that.
Now let's go ahead and take a look at something in context.
Let's try this out. So, here's the example. A standard chessboard contains 64 squares. Actually, this is just a number. This freaking thing is in the way. Number of unit squares. How many squares of all sizes are on that chessboard? If we get a question like this, will I be able to answer it? Start with the smaller boards. 1 by 1, 2 by 2, 3 by 3. Find a formula for the total number of squares in an n by n board. Well, how do you do
A
this?
standard 8 by 8 chessboard contains 64 squares. We know that, right? 8 rows of 8 columns would be 64 individual squares. Actually, this is just the number of unit squares, right? The 1 by 1 squares. How many squares of all sizes are there on a chessboard? Start with smaller boards, 1 by 1, 2 by 2, 3 by 3, etc. Find a formula for the total number of squares in an n by n board. Okay, so first of all, let's think in terms of
X and Y.
sequence.
Oh.
If n represents the dimension of a square board, so 1 by 1, 2 by 2, etc., then a sub n will represent the total number of squares of all sizes that we can create for that board. So let's look at an example. 1 by 1. All right, well, 1 by 1, there's 1 unit square, and overall, that's just 1 square. So there's only 1 square you could possibly form out of a 1 by 1. Not very interesting. For n equals 2, now we would have a 2 by 2, and let's think about this. We have a 2 by 2, which already has 4 squares, just by the fact that we can count them. But then you could also form a 5th square, which would be the entire 2 by 2 itself, right? So you have these 4 smaller squares, and then you have this 1 larger square. You can't have a rectangle. It can't be like one of these dominoes, because that's not a square, that's a rectangle. All right, so that means we have 5 different squares. Again, 1, 2, 3, 4, and then 1 big square. Now let's look at a 3 by 3. It's where things begin to get a little bit more interesting. And so we'll draw a 3 by 3. We know this already has 9 squares. And then it's going to have anything that's a 2 by 2 is also a square, right? So I have 9 squares individually. Then I have this square right here. I can take that. That's a square. Then I can shift that down 1 row, and I get another square right here. Okay, so that's already 11 squares that we can form. And then, of course, I can do the same thing over here. If I just shift this green square to the right 1 column, then I have a square there. So that's 12. Also, I can shift that one down. That's 13. And then I have the big square all the way around, right? So there's 14 squares that I could form out of it. Now, you can see how complicated this can start getting, because writing a function for this is difficult without having some numerical data to use. Let's do one more, and then we could start to analyze whether or not we have, whether this is a delta k constant sequence. So for a 4 by 4, let's divide in half and then divide in half again to get our 4 columns. Divide in half again. So we have 16 individual, and I'll just kind of keep tabs down here. Then we can have this square just like we did with the 3 by 3. There's plus 1 more, so there's 17. Shift that down 1 row, there's 18. Shift that down 1 more row, there's 19. Okay, now I could, so that means within each column I could have 3 2 by 2s. I'll just say plus 3 there. Now imagine that we take this entire thing and we just shift it over 1 square. So now we're focusing on the middle stack. And again, we'll have 1, 2, 3. So we'll have 3 more there. And then we can take that entire thing and shift it over 1 square. And then we'll have 3 more here. 1, 2, 3. All right, now we can also have 3x3s inside of a 4x4. So you can see this is a little bit more elaborate. So let's see how many 3x3s I have in this 4x4. Here's one, starting at the top left corner. Now I can shift that down 1 row, and there's a second one. And now, well, okay, I can shift that 3x3 over 1 layer, or over 1 column, and then I can repeat the same thing, and I'll get 2 more 3x3s, namely this one and this one. That's all the 3x3s I could have in there. Now I have also the big outer one, the 4x4. So that's yet another way I could form a square of any size out of this. So we get plus 1 more. Now let's count this all up. So we have 16 plus 9 is 25, 27, 29. We have 30. 30 squares inside of a 4x4 of all sizes. Okay, I think we have enough data to at least check our differences. Now, I already see that the differences are not constant. So if I analyze 1, 5, 14, 30, I look at the differences, 4, 9, 16. If I look at those, I get 5 and 7. Okay, those aren't constant yet, which means that I need to look at a 5x5, because if I do the third difference, I can't see if the third differences are constant because there's only one of them. So if I had another value right here, and I could get a difference there, then I could look at the difference between those two and look at the difference between these two. And as long as I get a 2 there as well, then I'd be good. But the problem is I need that 5th value. So let's look at a 5x5 and see if we can sort of expedite this. 2, 3, 4, 5, 2 by 2 here. And then I could shift it down to a second one, shift it down to a third one, shift it down to a 4th one. So there's going to be 4 of them here for these 2 columns, then I'll have 4 more here for these 2 columns, then I'll have 4 more for these 2, and 4 more for these 2. So that's going to give me 4 plus 4 plus 4 plus 4 is 16. 16 2x2s. Now I move on to 3x3s. Okay, so for 3x3s, I'll have, use some different color. I have a 3x3 here, and we can shift that down twice. There's a 3x3, and there's a 3x3. So I have 3 3x3s in that column. Now if I look at these 3 columns, I'll have 3 more. And then if I look at these 3 columns, I'll have 3 more. So that gives me a total of 9 3x3s. And now I have to look at 4x4s. Well, if you haven't noticed, then as we go higher, as we go one for a 4x4, when we looked at a 3x3, there were 4 of them. And that's going to be because with 4x4s, we can only shift down 1 time before we bottom out. So here's a 1, 2, 3, 4. A 4x4, and then I can get another 4x4 if I shift that down. So that's going to give 5x4s. And then if I take everything and just shift it over to these 4 columns, I'll get 4 more. So you see, we also get 4 of the just smaller size than the 4x4s than in the 5x5 that we're in. And then how many 5x5s? Well, there's just 1. So if you can see that here we add 16 plus 9 our data here now that we have 5 data points, and we could enter them just like this. We're going to start with n equals 1, and let's go ahead and do that in our table. 2, which means that we have a delta k constant polynomial. And in our similar vein, we could take our data here now that we have 4.33, repeating is going to be 1/3.
It's already 2 in the morning.
One question we may want to address is what happens when our sequences are not polynomials? In other words, what if we don't have a delta k constant polynomial? Okay, so not constant differences. If I look at the differences of those, I get 1, 2, 4, 8, and that's going to be 16. And then if I look at the differences of those, I'll get 1, 2, 4, 8. If I look at the differences of those, I get 1, 2, 4. And you probably get the idea now that as I continue migrating downwards, if I had more values going this way, then I would just have 1, 2, 4, 8, 16, etc. after that very first row. Now, something interesting happened here, and that is that it took until the second difference to start seeing this 1, 2, 4, 8, 16 pattern. By the way, this
It's weird. Huh. So it goes by my default system settings, I guess. Yeah. That's kind of annoying. Well, I'll play a little. This is a song I just finished. I want it to be longer, but I don't know what to add to it. That's kind of my problem with these kind of things. Is I write some songs that I think I like a lot, but then I just don't know how to like make them longer. You know, like this one's like 1 minute and 50 seconds, maybe. I can't even remember it. I will hold you again. I will be there, my friend, in case you need helping time of your life. The time of your life. We all were young before. Then we grew and learned to ignore the love we've lost. So we're scared to ask for more. But I won't let you fade away, 'cause you're special in a way I've never seen before. And I want more. And I want more. And I want more. So that's all I got, and I want to add more to it. I want more, as I was saying. But I don't know what to attach it. I could just get harder on the C chord, but no. It feels like a perfect stopping place, but I also don't want to stop there. It's too short. I know this note doesn't actually line up perfectly. Sorry, guys. I'm just trying to remember an old tune. Oh my god. Let's find another chord to go to. I'm a little stuck. Oh. Okay. Back to work. Letting myself get a little distracted and carried away now. Alright. If you guys hear my gum chewing, you don't have to deal with it. Let me know. Okay. Don't tell me it's 3. No, it's 2:30. Okay.
Tends to happen when your data is exponential, where each of the values are, say, powers of 2.
Now in this case, we do have, 1 is a power, so it's 2 to the 0. 2 is 2 to the first, 4 is 2 squared, 8 is 2 to the third, and 16 is 2 to the fourth. But we didn't see that emerge right away. Let me show you a case where you have a perfect exponential function, 2, 4, 8, 16, 4. So if you look at these guys, the difference happens immediately, or the 1, 2, 4, 8, 16 happens immediately in the first difference, and then it continues to be the second difference, and the third difference, and the fourth difference, and then of course now it doesn't get interesting because eventually we run out of differences that we can take without expanding these values. Now in this case, what I actually see is that this function, this sequence, will be 2, where this would correspond to n of 0 and so on. Okay, but it's not always that obvious, and the base doesn't always have to be 2, but if you do see that you get a repeated row after row after row eventually, there's a good chance that the data is exponential. So what we would do is what we can try is to find either use method of iteration, or if we want to try to do some regression fit to this data, let's input it and let's see how we can play around with exponential regression, as well as sometimes there's going to be exponential and polynomial terms being added. So here I am, and here I have those points in Desmos, and this doesn't look, it could at first look somewhat parabolic, but it doesn't quite have that bowl shape. It looks like it starts to really accelerate in the increase in outputs by the time you get to n equals 6. So if we begin modeling this and we try to get the regression, and we tried maybe a cubic polynomial, n cubed plus b n squared plus c n plus d. Well, you can see we get pretty close, but our r squared is not 1. And even though you might say, well, that's really, really close to 1, that may be really, really close to 1 for just these points. If you start generating more of them, you probably will start to diverge from the cubic polynomial. So the reason we want a perfect fit is these are supposed to be integers. We're generating integers in sequences most of the time. And if you don't get a perfect fit, that means you're going to be approximating some of those values. And that may be detrimental, especially if you're using this to write some sort of code or program where you need to have precision. So this is precision, but it's not enough precision. So let's just entertain the idea of to represent my base, because I don't know what the base should be, but I'm going to assume that it's some base to the nth power. And right now it looks like our r squared is worse, but notice that this does pick up a lot faster than this guy here. Now one thing that we know about exponential functions is the coefficient of that may not necessarily be 1 as we have it right now, but it might be a times b to the n, and in this case, notice that we're getting a lot closer, 0.9987. So in this case, it's saying it's about 3.17 times 1.72 n power. Okay, so if an exponential by itself is not enough, well then we might say, well perhaps it's an exponential plus a polynomial. So a great place to start is to say plus c. Maybe we're just off by a constant. Well, clearly that doesn't do it. That doesn't get us to r squared of 1. So let's just say we'll have a linear term, c times n plus d. Okay, so notice that I have an exponential plus a polynomial. N is my variable. exponential. So how would I do exponential? Well, the way I'm going to do exponential is I'm going to I'll use b to represent my base, because I don't know what the base should be, but I'm going to assume that it's some base to the nth power. And right now, we see that r squared is worse.
These, my friends, are zero nicotine, zero caffeine. Beautiful little things.
May not necessarily be 1 as we have it right now, but it might be a times b to the n. And in this case, notice that we're right some sort of base, because I don't know what the base should be, but I'm going to assume that it's some base to the nth power. And right now, it looks like our r squared is worse, but notice that this does pick up a lot faster than this guy here. Now, one thing that we know about exponential functions is the coefficient of that may not necessarily be 1 as we have it right now, but it might be a times b to the n. And in this case, notice that we're getting a lot closer, 0.9987. So in this case, it's saying it's about 3.17 times 1.72 to the n power. Okay, so if an exponential by itself is not enough, well, then we might say, well, perhaps it's an exponential plus a polynomial. So a great place to start is to say plus c. Maybe we're just off by a constant. Well, clearly that doesn't do it. That doesn't get us to an r squared of 1. So let's just say we'll have a linear term, c times n plus d. Okay, so notice that I have an exponential plus a polynomial. N is my variable, my input variable. A, B, C, and D are quantities that I want Desmos to estimate. Well, check this out. Now we're officially at r squared 1, meaning we have an exact fit for those data points. And so this suggests that our equation should be of the form 1, so really just 2 to the n power plus 3n. So if we plot y equals 2 to the x plus 3x, now because I'm graphing a function, I do have to use that. Notice that these are exactly the same function, so the solution to our recurrence relation over here is going to be a sub n equals 2 to the n plus 3, which is 1 when you're dealing with these discrete constant terms. Maybe I would do cn squared plus dn plus b, and let's see, what did I do? D times n. Oh, e, it's actually, can't use e. E is Euler's constant, so we'll use f. And in this case, notice what it does for c and f. So for the quadratic and the constant term here, it's well, effectively they're both 0. C and f are both 0 because 1 times 10 to the negative 14 means it's 13 zeros followed by 1065. So these are effectively, C and f are effectively 0. There's a lot of software that estimates there's going to be some round off error. But C and f are pretty much 0, and again, we just get 1 times 2 to the n plus 0n squared plus 3n plus f. So really, we didn't need the quadratic. And so you can kind of start with a cubic or quadratic polynomial, and maybe the quadratic piece or the cubic piece will just end up being 0. So it never hurts to add those terms in there. We're always looking for an r squared of 1.
Okay, so we finished lesson 16. On to lesson 17. We have 17, 18, 19, 20, 21, 22. That one I took probably a little too long on. I want to go to bed. I'll be honest with you, I want to go to bed right now. I'm a little bit tired. Oh dear, this one has a lot of videos. Let's see what ChatGPT said, because I also had ChatGPT mock me up a cheat sheet based off the lessons that I gave to it. Excuse me. Let's see. Because I made my own lesson for 16, and let's see how it lines up. Yeah, if I just turn this down. And to any new viewers, welcome and enjoy the relaxation. It's going to be a quiet night tonight. Just studying, but if you need a study partner, you can leave this open and study with me.
Welcome. In this video series, we're going to talk about algorithms and complexity. So typically when we write code, especially when we're writing bigger programs, we want to know how efficient our code is. So we're going to do some operation counting, meaning we're going to have to count the number of operations that code will accumulate in the worst case scenario. So that's really key here. There are other types of analysis. There's the best case analysis, the average runtime analysis. We're only going to consider the worst case analysis here. So to keep things really simple, we're going to only assume that the following count as floating point operations. In fact, each one of these things will count as one floating point operation. We're just going to call this flops for floating point operations. So anytime we're going to make an assignment to a variable, anytime we do any arithmetic, addition, subtraction, multiplication, division, we're really going to limit ourselves to these things. So anytime you see an assignment to a variable, that's going to count.
Okay, so just in case anybody is curious, right now, and the reason I explain it is because it makes it shows me where I do not know things and what I do know. So right now, and even if nobody's listening, I kind of just feel like people are. But anyways, we're doing lesson 17. We're doing our cheat sheet right now on lesson 17. Actually on lesson 16 through 22 because we got the final tomorrow. Right now we're doing lesson 17, which is algorithms, and complexity. So the first part is counting flops. So, which is I think this is going to be like a lot of pseudocode type stuff.
Or one flop. Anytime something is added, it will count as one flop. So let's take a look at this line of code and see if we can conduct this analysis. In this particular analysis, we have a function called sample function. It has one input variable called n. And then
So a flop is a floating point operation, which means it's a single arithmetic calculation such as addition, subtraction, multiplication, or division, involving real numbers, numbers with decimal points or exponents. And this question, this example here says, when we write code, we would like to know how efficient it is. Thus, we need to count the number of operations required to execute the code. In the worst case scenario, to keep things simple, we will assume each of the following count as one floating point operation. So, assignment to a variable, addition, subtraction, multiplication, division. Okay, multiplication, division. Multiplication. Probably don't need to write that down. My day was great. I mean, it's still going. I probably got a few hours left of it. How was your day? Well, thank you for the follow. If that's what that was. Yeah, I appreciate that. I don't know why it didn't pop up on my notification thing. I guess now I understand it's only connected to Kick. Kick must be YouTube, I think. But yeah, how was your day? How many flops will the following lines of pseudocode require? So def sample function, okay. Define sample function, and
all as flops for floating point operations. So anytime we're going to make an assignment to a variable, anytime we do any arithmetic, addition, subtraction, multiplication, division, we're really going to limit ourselves to these things. So anytime you see an assignment to a variable, that's going to count as one operation or one flop. Anytime something is added, it will count as one flop. So let's take a look at this line of code and see if we can conduct this analysis. In this particular analysis, we have a function called sample function. It has one input variable called n.
okay, I'm sorry, I remember this. Yeah, I remember each input or each assignment and each arithmetic like operation, such as addition, subtraction, multiplication, or division, counted as one flop. I know he just said that, but I'm starting to remember it. I'm remembering doing it now.
Require one floating point operation. So right there, we'll have one flop. And now we're not going to worry about comparisons. Typically, when you do a more rigorous analysis, you do account for the fact this comparison has to take place, and it does.
So when I'm going to write down when counting flops, unless specified otherwise. Do not count comparisons such as n, such as if n is greater than k as one flop.
Take some time to do that. Now, again, we're doing the worst case analysis. So that means if this is not going to count as a flop, we have to ask ourselves, well, suppose that if that condition is satisfied, suppose that n is in fact bigger than our k value, that what the user inputs is in fact bigger than our k.
Yeah, so we're doing the worst case scenario, which means, did I mute myself by the way? Anyways, worst case scenario, which means given some line of code or an operation that we want to complete. Oh my god, I feel like I look tiny right now. This is not okay. I need to get back in the gym. One more day. Tomorrow's my last day. Finals, I get back in the gym. I'm so excited. I mean, I'm kind of dreading it. I've had this feeling quite a few times where it's been like 2 weeks since I've last worked out, 2-3 weeks since I like was on a good, whatever, consistent thing. And every time I get this feeling, but now I'm so familiar with that feeling that it like honestly doesn't bother me too much. Of like feeling this like almost like what's the point type thing. Like I'm already feeling so much weaker than before. It's like letting go basically. And before when I was younger, that might have stopped me from going back. But I've gone back enough after like I just didn't have time to work out for a couple of weeks. And every time I felt this, it's like I feel like once you become more familiar with that feeling, it's a really healthy thing because when you have that kind of demotivating feeling of like, yeah, well, what's the point? Or honestly, like, I haven't worked out for 2 weeks. Why continue? Like, whatever the you get, that's kind of this like air of demotivation. And when you conquer that over and over again, and I'm not saying I've done great, I've had so much success in my life, but when it comes to the gym, I have had many times, especially in the last 2 years since I started working really hard, we're working out really hard, pretty hard, I should say, where I had like 2 weeks, because I work out pretty hard, but at the same time, I don't stress too hard about it. Like if I have something to do that's very important, and I'm gonna get like 6 hours of sleep versus 8 hours if I work out, I'll get the 8 hours of sleep because I think it's more healthy for my mind while I'm studying to get those 8 hours of sleep. But granted, whenever I have time, I'm not gonna play video games if I don't have. I mean, there's been a couple times I'm sure I have, but I'm not gonna have fun doing other things if I have a full free day before I work out. And so that's kind of how I see it. And I feel like it's a great way to approach it because there's a lot less stress. It does suck on those 2 weeks. Like I probably could have worked out if I made it a super hardcore goal of mine, but I needed to study and all that, and so it does make it I think a little less stressful on yourself when you say, hey, I'm going to work out, but you commit to that whenever I have like actual free time. Anyways, I'm going on now. I digress. Back to work. So a flop, what we're saying is, in this case, in these examples, I'm sure during the test it'll be like this too. We're going to be counting worst case scenario. How many flops do we need if all those lines of code were ran? Like if all the if lines were satisfied, and all those while lines were satisfied.
And something's going to happen, and that's going to require some time for that thing to happen. Here we.
So this is going to be one for assignment. If this does happen, that's going to be a second assignment plus an arithmetic. So that's 2 flops. And that's 2 flops. So we're looking at 5 flops.
So all we have down. Okay, so this says from 0, and that's going to give us 2 flops.
Oh. So if an operation is completed X amount of times i.e. from 0 to 10.
And when and then how many iterations are we going to have? We're going to have 11 or 22.
You will count the flops. You'll count the flops for each of those iterations. Count the flops for each of those iterations. All right. We'll donate for booty. Follow me. I just noticed the name on that. That's hilarious. I thought it was the bot guy that was talking to me. Well, I think it's a bot. Whenever they say, "Hey, how's your day?" I assume it's a bot of some sort, because now I've gotten so many what's called summary messages where they start off, "Hey, how's your day?" and whatever. I live in Virginia, and if you drop your Discord, I'll create custom art for you. And yeah, I think the rest is history. I think we all know that it's a scam of some sorts. Anyway, so what we learned here is that if we have a line of code we're trying to count at worst case scenario, what or how many flops we're going to be needing, and these flops being a floating point operation. And in our case, the things that we're probably going to be counting on the test are going to be an assignment to a variable or an arithmetic operation, being addition, subtraction, multiplication, division. And we're probably not going to be counting comparison operations like if n is greater than k. All right. So the biggest takeaway from this is, because I remember this is what I messed up on something before, if there's multiple iterations, like it says for I from 0 to 10, you're going to be counting the flops for each. That's probably, I know, pretty self-explanatory, but you're going to be counting the flops for each of those iterations, and then you add them all together.
Flops in total. And so we had to have one flop here, two more flops here, 22 flops here. So when we add those together, our worst case runtime is going to be 25 flops. Now that's the worst case scenario. The best case scenario is, of course, this is going to happen no matter what when we call this function. Same with these 22 flops down here.
Let's see something. Okay. I wonder why. Just because I've been trying to get this thing set up for a while, and I wonder why the follow didn't show up on the thing. I wonder if it's the name. I wonder if it like auto stopped it. If there's something built into that code that stops certain words. Who knows? All right, back to work here.
And the runtime would be 23 flops instead of down here. The only thing that can vary is that if n is not greater than k, then we get to save 2 flops, and the runtime would be 23 flops instead of the 25 that we ended up with here. In this next example, we're going to do the same thing. How many flops will the following pseudocode require? So our function here is called.
Okay, so let's do it. We got 1 flop here, count equals 0. That's an assignment. For I from 0 to, oh, I remember this is what confused me. 0 to n, so the nth number. For j from 0 to 2n, oh yeah.
Again, it has an.
This is where I'm going to need my notes.
The first thing that we're going to do is we're going to make an assignment, so that's going to require 1 flop. And
I'm going to mute myself while I eat some chips.
so in this nested loop, we have to think about how many times this is going to run. We want to go inside of the body of the innermost loop because this is an easy count. This is going to require 2 flops, but that's going to be per iteration.
Ooh, 2 flops.
One iteration. Every time this function runs, 2 flops are going to take place. The next thing we need to determine is how many iterations will there be. Well, this innermost loop, when we kind of back our way out, we work our way out, this is going to run from 0 to 2.
Damn, that's spicy. I mean, it's not that spicy, but it's spicier than I expect. These things are so good. And they get, like, the more I try to act like they're not spicy, the more spicy they get for some reason. It's a weird effect. All right, so what we're going to do here, all right, is go over more flops. Okay, so we have, I remember now, this is my point of confusion, from count the flops for define sample function 2, count equals 0 for I from 0 to n. 0 to n. So let's see what he says.
This is going to run for 2n plus 1 iterations. Why is it 2n plus 1? Because it starts at 0, and
Yeah, that'd be one
we're
flop.
starting at 0, we're counting 0, but then we're going 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 2n plus 1. Now this will run 2n plus 1 times to 2n. So that means it's going to have, it's going to start at 0, we're going to include 0, and then we're going to go 2n more times. So this is going to run for 2n plus 1 iterations. Why is it 2n plus 1? Because it starts at 0, and we're starting at 0, we're counting 0, but then we're going 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 2n plus 1. Now this will run 2n plus 1 times, but then those 2n plus 1 iterations will be performed n times. So n iterations. And so an easier way to think about this is, suppose, like, for example, let's say we assign n to be 1 to keep this really simple. So the first thing that's going to happen is I is going to be assigned 0. J is going to be assigned 0. And then there's going to be 2 flops. So we'll keep track of the total number of flops here. Now the next thing that happens is I stays 0 because we're going to go down this way. This is going to run now, and so that means J is going to increase from 0 to 1. So I will equal, now in this case, 0, excuse me. J is increased to 1, and 2 flops will take place. Now, so since n is 1, 2n will be 2.
Wait, I gotta rewind here.
Well, this innermost,
I'm gonna chew a little bit with you guys on here.
this is going to run from 0 to 2n. So that means it's going to have, it's going to start at 0, we're going to include include 0, and then we're going to go 2n more times. So this is going to run for 2n plus 1 iterations. Why is it 2n plus 1? Because it starts at 0, and we're starting at 0, we're counting 0, but then we're going 1, 2, 3, 4, 5, 6, 7, 8, all the way up to 2n plus 1. Now this will run 2n plus 1 times, but then those 2n plus 1 iterations will be performed n times. So n iterations. And so an easier way to think about this is suppose, like, for example,
I don't understand why it's 2n plus 1 iterations when we have j running from 0 to 2n, but for I from 0 to n is just n iterations. I don't understand why it's not n plus 1 iteration.
we assign n to be 1 to keep this really simple. So the first thing that's going to happen is I is going to be assigned 0. J is going to be assigned 0. And then there's going to be 2 flops. So we'll keep track of the total number of flops here. Now the next thing that happens is I stay 0 because we're going to go down this way. This is going to run now, and so that means j is going to increase from 0 to 1. So I will equal, now in this case, 0, excuse me. J is increased to 1, and 2 flops will take place. Now, so since n is 1, 2n will be 2 times 1, which is 2, so we still have one more index value to go.
A series. So if I have a series. What's up, bro? Wealthy Live. How you doing? If I have a series of what was I saying? A series of what's the word for something that depends on the thing that happens before it? I should know this. What is the word for something or for a number in a series that depends on a prior number? A recursive relation. Yeah, that's what it is. Recurrence relation. Yeah, well, live. How you doing? How you doing? Welcome to the stream. It's super exciting right now. We're getting my cheat sheet ready for my final tomorrow. Actually, starting after tomorrow, it will be pretty fun because I will be able to, actually have real streams where I have some buddies on. It'll be a little bit more exciting. But tonight, I have you guys on so you can study with me, ask me whatever questions you got. And honestly, it motivates me to just have the stream going while I study because I get distracted super easily from the piano back there and my guitar over here and whatever I can find, whatever I can get my hands on. And yeah, so it kind of helps me to study while I have some people watching because it kind of keeps me accountable just a little bit. And then if you guys want to study alongside, I know some of you might have finals going on too. If you feel like you need a study buddy, feel free to keep this on, play some lo-fi, and get to studying. Alright, so if we have a series of, I'm just going to say, like functions. A series of functions. You can calculate the amount of flops needed by setting up something like this. Oh shit.
I will be 0, J will be 2, and 2 flops will take place.
Now that we're
Wait.
out of J values, we've reached J
Let's see.
equals 2 since n equals 1. Now we're going to go back up here. Now that we're out of J values, we've reached J equals 2 since n equals 1. Now the next thing is iterations. And so an easier way to think about this is suppose, like, for example, let's say we assign n to be 1 to keep this really simple. So the first thing that's going to happen is I is going to be assigned 0. J is going to be assigned 0. And then there's going to be 2 flops. So we'll keep track of the total number of flops here. Now the next thing that happens is I stay 0 because we're going to go down this way. This is going to...
What was that? I just got a notification. Oh, hey, thanks for the follow. I appreciate that. You're helping build the coolest, most badass community there's going to be out there. We'll see. But yeah, I appreciate that. I don't know if you saw earlier, but you gotta try those things. They're so good. A little spicy though. A little bit spicy. It's a powder on them. The powder kind of is a little bit loose and goes flying through your throat. Anyways.
To run now. And so that means J is going to increase from 0 to 1. So I will equal...
I did get some, oh, you're from Kenya? That's badass, man. That's far away from me. It's probably, is it daytime over there, I'm guessing?
Now, in this case, 0...
I need to get some kind of, like air horn type thing, so when somebody follows me, or maybe something on the screen, and then I just, like, you know, press a button, make a whole thing out of it.
A is increased to 1, and 2 flops will take place.
We're doing some discrete mathematics right now, by the way.
Since n is 1, 2n will be 2 times 1, which is 2, so we still have one more index value to go. I will be 0, j will be 2, and 2 flops will take place. Now that we're out of j values, we've reached j equals 2 since n equals 1. Now we're going to go back up here. I remains 1.
Okay, I'm a little confused though.
Example, let's say we
Sorry, I'm a little confused.
To be 1.
Let's see, so
So the first thing that's going to happen is I is going to be assigned 0. J is going to be assigned 0. And then there's going to be 2 flops. So we'll keep track of the total number of flops here. Now the next thing that happens is I stay 0 because we're going to go down this way. This is going to run now, and so that means j is going to increase from 0 to 1. So I will equal now in this case 1.
now, okay. So what it looks like we're doing here, we are going to run through the iterations. So now. Run through iterations until code is complete. So code is complete. Once complete, add up all flops.
It is increased to 1, and 2 flops will take place. Now, so since n is 1, 2n will be 2 times 1, which is 2, so we still have one more index value to go.
And I will have you know, Weldy Live, and anybody else who's watching that, I want to know more about you guys too. And so after my finals are over, I'm going to be getting on with some friends and all that. And we'll have you guys, all will be on live, and we'll be taking questions, and it will be a lot more participative. Right now, I've just got this set up here really recently. So I just have it running kind of for the heck of it, and all the other things I mentioned before, just like helping me focus. But if we do plan on making this a more exciting, not extremely, we don't want to be, like fake, but just it's gonna be like I'm gonna be on here when I'm actually having fun, so that'll be more exciting. Just want to put that out there because right now I know studying discrete mathematics may not be the most exciting thing, especially when I can't really even share my screen or none of that.
I will be 0, J will be 2, and 2 flops will take place. Now that we're out of J values, we've reached J equals 2 since n equals 1. Now we're going to go back up here. We're going to increase the counter from I equals 0 to I equals 1. And so this is our last index value for I, because I goes from 0 to 1. So now J resets, and J becomes 0. And so now we're going to do 2 flops. I remains 1. Now this is going to back up, increase the value of J. J becomes 1. And this is going to require 2 flops. I remains 1 while J increases to 2. And we'll add 2 more flops, and that's 2 plus 2 plus 2 plus 2 plus 2. That's 6 times 2, which is going to require 12 flops. Now, if you notice that really becomes the value for I, because I goes from 0 to 1. So now J resets, and J becomes 0. And so now we're going to do 2 flops. I remains 1. Now this is going to back up, increase the value of J. J becomes 1. And this is going to require 2 flops. I remains 1 while J increases to 2. And it'll add 2 more flops, and that's 2 plus 2 plus 2 plus 2 plus 2. That's 6 times 2, which is going to require 12 flops. Now, if you notice that really what happened here is this thing here ran, we said n iterations is actually n plus 1, because we're including 0 once again, so it should be n plus 1 iterations. So notice what we really did is this ran twice. The inner loop ran 3 times. 2 times 3 is 6. That means there'll be 6 total iterations of 2 flops. 6 times 2 is 12. So what really happened is, if you think about it, this is kind of iterations per iteration. I'm sorry, other way around. This one here, in the inner one, is how many times this will iterate 2n plus 1 per iteration of outer loop. And this is n plus 1 iterations of the outer loop.
Okay, my phone go off.
The inner one
I did.
is how many times this will iterate 2n plus 1 per equals 0 to I equals 1. And so this is our last index value for I, because I goes from 0 to 1. So now J resets, and J becomes 0. And so now we're going to do 2 flops. I remains 1. Now this is going to back up, increase the value of J. J becomes 1. And this is going to require 2 flops. I remains 1 while J increases to 2. And we'll add 2 more flops, and that's 2 plus 2 plus 2 plus 2 plus 2. That's 6 times 2, which is going to require 12 flops. Now, if you notice that really what happened here is this thing here ran, we said n iterations is actually n plus 1.
Okay.
Because we're including 0 once again, so this should be n plus 1 iterations. So notice what we really did is this ran twice. The inner loop ran 3 times. 2 times 3 is 6. That means there'll be 6.
I thought it was n plus 1.
2 flops. 6 times 2 is 12.
That makes me feel better.
So what really happened is, if you think about it, this is kind of iteration of outer loop.
Been having way too much gum lately.
And this is n plus 1 iterations of the outer loop. Okay, so this is going to iterate by itself, but it's going to be repeated n plus 1 times. So if we do the math on this, we can see that it's going to require 1 flop up here, plus it's going to require the 2 flops. going to put this over here, but we need to count how many times those two flops are going to take place. Well, on the innermost level, they're going to take place 2n plus 1 times, and then those things are going to occur n plus 1 times in total. So really what it boiled down to is multiplying these two values together. That's going to give us the total number of times we're going to perform two flops. So if you do the dimensional analysis on this, this is iterations of outer loop, iterations of outer loop. This is going to be iterations per iteration of outer loop. And this is going to be flops per iteration. And so now these units cancel, you can see that we're counting the total number of flops. So our final answer is can be written like this: 1 plus quantity iterations per iteration of outer loop. And this is going to be flops per iteration. And so now these units cancel, you can see that we're counting the total number of flops. So our final answer is can be written like this: 1 plus quantity n plus 1 times 2n plus 1 times 2. Now we're doing a little bit of expansion on this, and we're going to see what.
So, it turns out, sorry if you guys hear the gum, just take it as a little bit of ASMR. But it turns out you can multiply the iterations. That might be an easier way to get this all done.
Do this if I do some and all that stuff, but this would be our time complexity function. So the output of this should be the number of flops. The input is the number of times.
Oh. So the time complexity function is a function whose output is the total number of flops. Whose output is the total number of flops required as a function of any input variables. Okay, that's pretty simple. I know the chewing is annoying, if you can hear it, but I'll be right back. I have to urinate, so give me a second. Oh my god. Okay. was just my best friend. Just talked to him for a little bit. Okay, number of, what was I saying? Number of flops. Oh, damn, I started, oh. Okay.
So as our checkup here, we noticed that this would have required this particular example when n was equal to 1. We would have had 1 flop here plus the 12 more flops. That's 13
Dude, I think I'm getting like a
flops.
little pimple right here.
Let's
That's
double
the
check that
worst.
our function tells us the same thing. T of 1 would be 4 times 1 squared plus 6 times 1 plus 3, which is 4 plus 6 is 10 plus 3 is 13, and that matches exactly what we got up here. Here we just now have it symbolically so that we can count the number of total operations for any value of n. Now the one interesting thing to note is that if you were to graph these functions and you were to take a look at them as the value of t versus the value of n, here no matter how big of a value the user inputs, and I'm going to kind of skip some lines here, but the runtime of this function is a constant 25 operations. Again, we're assuming worst case here from both instances. But here what happens is I have to run more and more flops, or I have to perform more and more flops as the size of n increases. So in this case, we're going to have a quadratic function that we know that starts to grow more and more rapidly. So this particular code will become less and less efficient as n gets extremely large. You can see this thing will just continue to blow up at a quadratic rate. In the next video, we'll start to think about order of these guys.
The big O notation.
In the previous video, we started writing time complexity functions for a variety of small algorithms, and now we want to talk about the size of this time complexity function. So we argued that a constant time complexity function has a constant order, really. The number of operations will be 25 regardless of the input size. But in our example 2, because we had a nested for loop, we ended up with a quadratic function, which as n gets really large, the time complexity rapidly increases. One of the trade-offs as time complexity rises with that, so, well, based on the structure of the time complexity function, this leads us to describing its order. For time complexity functions with only one term, for some constant c and input variable n, we'll talk more about this soon, we can describe the following orders. So if your time complexity function is a constant, we say that it's constant order. And we usually write that with this big O notation. We won't get really heavy into the mathematics of the big O notation, but we would write that
Order of a complexity function. Is of a constant order. So T of n equals C is of a constant order, written O of C equals 1. Okay. Linear C of n, or Cn, is linear order. Written O, C, and N equals N. Cn squared, quadratic order, I'm sure. Yep. Quadratic order. Written O of C of N squared equals N squared. And we got cubic. I'm sure cubic order, yep. Yeah, written. Okay, O of C and N cubed equals N cubed. Logarithmic order. Log N. Okay, and here we got the last one. Exponential order. CB of N. Guessing B of N, yeah. Oh, hey. I don't know if you're still there. Rocker. ROKR. Sorry, I'm a little sidetracked right now. I'm on my main quest right now. I'm main questing it. Trying to, trying to study for my finals. Oh, I don't speak that. Arabic, I think. I don't speak that or read it. But I can read English. But I'm studying some discrete mathematics. Right now we are going over algorithms and time complexity, which I think sounds more complex than it really is. Are you able to hear me? Can everybody hear me? Can everybody see me? Well, ROKR. You now? You're new? What does that mean, my friend?
The order of a constant is 1. We'll get back at why we say this is 1. 1 is sort of the base constant. And all of these orders
1 is the base constant. Remember that.
So if your time complexity is some n, again, that's n is the simplest.
Okay, so
N squared. Again,
we're gonna go through all of these.
What I've provided down here is a graph of these various functions.
So we know what all these functions look like.
Or in example 1, that value of n was really never used other than to determine whether the if statement exists or not.
The question is,
The purple function here is.
oh, that's right, in terms of effectiveness.
So what I've provided down here is a graph of these various functions. And what we want to emphasize
emphasize here is certain functions will grow more rapidly than others. So in this, we actually have arranged from fastest to or most.
So 1. Log order is going to be 1. We'll say, okay, I'll just do it right here. Fastest. Two, 3. X squared is 4. And then x cubed is 5. And 3 to the power of x is 6.
Efficient to least efficient. So I'm going to write that right up here. We'll say that this is the most efficient.
Most efficient. ROKR, you still there, man?
To the least efficient.
Man or woman?
By least efficient.
And what were you saying?
For the least efficient ones, Tn is going to blow up much faster. So Tn is going to be really huge.
I'm going to translate this.
Inputs, but Tn is going to be typically pretty small here for large inputs. So when we take a look at this graph, we see that the purple function. So let's think about the x-axis.
He said, I know you idiot. Well, she. Why are you talking with that if you know? Let's translate this one too. Based off the images I'm seeing when I look it up, it's not going to be a happy one. Your leg is in my throat. What does that mean? I feel like it might be, the translation might be off. I think I might get what you're getting at. All right, well, let's take that energy and put it to some mathematics here. All right, so
operations or iterations of a loop. We can see that the next most efficient, as n gets increasingly large, is this black one here. And that black one is logarithmic. I have these mixed up. This right here should be x log x.
You son of a bitch. Excuse my French.
So you can see that.
All right. This is why I should do my notes in pencil, but wait, what?
Example 1, that value of n was really never used other than to determine whether the if statement would execute or not. So you can see that the purple function here is the most efficient. And what we mean by most efficient is in the long run. So when you start to increase your input size, we call this in the long run. Because typically we are not running functions for 2 iterations or 3
Ooh, I was meant to.
real world things run a lot of time, maybe millions or on the order of millions of times. So we can see that although there's some weird stuff going on here where maybe there's one of the curves is lower than the other curves, what we can determine for sure is that this guy here is...
I'm doing good, and I don't want any custom art or anything like that, by the way.
The number of operations, notice
How are you doing?
10 or 11 operations.
I ask that only if you are not offering me custom art and logos and all that good stuff.
Is this black one here, and that black one is logarithmic. I'm sorry, I have these mixed up. This right here should be x log x, and this right here should be x log n.
So, what?
Stretch out. I can't read my own graph. So
Zarabin.
gets sizably large.
Zanzibar.
Linear function is less efficient than the black function. Eventually, there's a crossover here, and that's really what we're looking after. That as n gets larger than 10,
I know.
the red function requires fewer operations than the black function. We can see that here, that this output value right there, for example, is smaller than that output value right there. And what do we mean by output? We mean the number of operations. So perhaps this one requires almost 11 flops, but this one only requires about 10 flops for the input size of 11. So this was okay. And then you could see that
Yeah. I ate quite a bit today. to get back to work here.
Performs worse in the long run than the least efficient of all of these. So you typically do not want to write functions of exponential order. You prefer to have something that stops right about here if possible. Quadratic order still behaves pretty nicely, but when you get into cubic, things blow up very rapidly. And by the time you get to exponential, those are some messy functions. They do take some time for your computer to run them. So this helps us in the following way. Why would we want to talk about these different orders? Well, a lot of times our functions, our time complexity functions, has a combination of terms, some of which are linear, some of which are quadratic, perhaps even exponential. Then the order of that time complexity function is the order of the most rapidly increasing term. Why? Because terms that grow faster than others will dominate as the input size n approaches infinity. That is, gets very large. So we're doing this long run analysis. There are other analyses that, maybe in the short run, if you're planning on just running
I will be there.
back here to this graph,
Do, 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 do. You guys know what I'm saying? Didn't that sound amazing? I will be there. Oh my god. I'm getting tired. Alright, I think this was a successful stream. We got 2 new followers. And I appreciate both of them. And to anybody watching still, feel free to follow. I'll be back after tomorrow, and we'll be done studying because the finals will be over tomorrow. So something to look forward to. So next time I hop on, it'll be a little bit more fun. Well, the live, actually, I'm just hopping off right now. I'm just getting off right now, and I was just thanking my new followers, including you. So thank you for following me. I am getting off. I have to go to bed. It's 4 in the morning because I am from Arizona in the United States, baby. So pretty far away from Kenya. But I do have to go to bed because it's 4 in the morning, and I have work tomorrow, and I also have my finals I have to take tomorrow. So in the meantime, you guys have a great rest of your day or night, wherever you are. I can barely think it's 4 in the morning. But I'll see you guys back, probably not tomorrow, because I have my finals tomorrow, but I think the day after that, I'll be back on at night.